This is lecture 17B. This is the last part of the last lecture of this series. Thanks for watching all of them. Thanks for joining me on this little journey. Well, we're going to finish up in this lecture about doing math in assembly. So this is doing math in assembly, part 2. So we saw before how to do basic integer math involving add, subtract, multiply, and divide. We talked about roots. And we began talking about integer ratios. We're going to talk more about integer ratios here. And then we're going to look at rudimentary fixed point calculations. Okay, so integer ratios and functions. So last time we looked at ratios, and it turns out for a number of different constants, we can have their decimal representation and also their 8-bit representation. So when I say 8-bit, that is, as a ratio, this ratio is approximately equal to that, and it's 8 bits in the sense it's dividing by 256. Okay, so we have different constants that we can use to different ratios we can use to represent some of these complicated numbers. If I have 16 bits that I can work with, then here's the 16-bit. So basically that shifts the whole thing over by 2 bytes instead of just 1 byte. This basically shifts things over by 1 byte. So anyway, those are some of the integer ratios we could work with. Now, if you had a particular number and you wanted to find a ratio, how would you do that? So in general, it's desired that you would find a constant. So for example, it can be an irrational number that you're working with for which you need a constant. So obviously we can't implement an irrational number anyway. So it's good to get a ratio to describe it. Or it may be that we're looking for a combination of constants, a whole product of a ratio or whatever of constants, and so we want to just kind of lump that in together and just get a single number that represents that. And generally we want that to be a 16-bit or an 8-bit divisor. Okay, so how would we do that? How would we start with a number and get, so like those approximations that I should do, how did I get those? How do you get those? How does anyone get them? Well, here's one way. We take the constant c, multiply it by either 256, which is 2 to the 8, or 65536, which is 2 to the 16, multiply it, round the result to the nearest integer, n, okay, and check to see if n minus 1 or n, the difference between that and the number, the constant you're looking for, whichever is smaller. See which, so that's kind of like the integer above, the integer below, to see if any of those are smaller. Which one has the smallest 8-bit error, so if you're dividing by 255, or if you use this, whichever one has the smallest 16-bit error. So this is how you would find such a constant. Okay, it's not rocket science to find it. You're basically finding the closest approximation. And since we're only going to divide by either 255 or by this number, then that's how we would find it. Okay, so now we've got integer ratios of constants out of the way. We're going to look at integer ratios associated with functions. So we'll start with the simple one, log base 2. That's kind of a weird thing. You probably never use log base 2. Well, so anyway, but it's an important function because it's related to other functions. So the integer value of a logarithm base 2 of a number is useful in determining the number of bits required to store a number. So if you have a number, 65537, how many bits does it take to store that number? If you take the log base 2 of that quantity, that will give you the number of bits. The integer portion of that is going to tell you how many bits. And so if you have like 3 points, that means you're going to take at least 3 bits, maybe 4. 3 point something. So if it's 2.9 something, then 3 bits should handle it, right? So this may be computed by shifting the number left until a 1 falls out. That's actually pretty straightforward. To compute the log base 2, we just take that number and we shift it left until we get a 1, a carry. Okay, so we do a left shift until we get a carry. So here is code that can be used to do that for a particular example. So as an example, I want you to work this out and see what happens. What's the result that we get out of all this? Okay, try it. Now that we've worked through the problem of natural log base 2, we can turn our attention to something that's perhaps a little more common, the natural log. So the natural log is often referred to as the log base e. And basically, we can perform the calculation of the natural log using this relationship. The natural log of x is equal to some constant times the log base 2 of the net. So the log base 2 of x can be used to give us the natural log of x. There's a constant here. That constant is 1 over the log base 2 of e, which is this number. Okay? And we have these various approximations we can use for that. So in order now to get the natural log of x, we would use the log base 2 of x, multiply it by a constant. So it's very straightforward. We have, and so remember the log base 2 now is just that left shifting that we're doing, okay, until we get the number of shifts basically tells us the log base 2. That's the integer portion of the log base 2. Okay, so I now multiply it by a constant, and incidentally, this particular constant can be broken up into these little parts for simpler calculations. Okay, so we have this way of dealing with integer ratios. The natural log. Okay, so all of this can be done using the log base 2, and then multiplying by this constant. Okay, so we've extended the simple function of log base 2 to the log base e. Okay, so remember, we're only talking about 8 bits here or 16 bits here, so it's not like we're working with the whole long expansion. But this is the approach we can do even if we don't have, for whatever precision, we can use this approach. Okay. Now here I have code that uses that actually does a computation of it, and I'll let you work on this. So this is your opportunity to work on a practical example of this. So go to it. Next, we move on to another common function, which is the log base 10. So again, the log base 10 is very similar to log base e. That's one of the nice things about logs, is they're all very similar. And basically, the log base 10 of a number is equal to some constant times the log base 2 of a number. And the constant in this case is the log base 2 of 10, which is this number. And we have these approximations that we can use for that number. Okay, so now we have a way of working with integer ratios that allows us to do the log base 10 of a function. And it's based again on this notion of the log base 2. So now we also talked about division and how division is related to powers of 2. And so here, if our denominator is a power of 2, it involves shifts to the right. And if we actually shift enough times, we actually drop a whole byte. Okay, and so here, if I'm continuing to divide, I drop the low byte and shift, drop the low byte and shift, all the way down to this point, in which case I drop the lowest 2 bytes. So obviously, I need to have at least 2 bytes if I'm going to even do this. So that's how we can avoid division. The This is actually doing division with these particular denominators. So we've now talked about integer ratios, and in the case if we can use powers of 2 as our denominators, that makes it very simple. So, integer ratios. Useful stuff when doing math on a limited processor like the Arduino. Next, we give a brief discussion on fixed point math. This is just a brief discussion. So in fixed point math, we have what are called fractional binaries. So again, we saw with the fractional binary that you can have parts to the left of the, we often refer to that as the decimal point. The technical definition is that's the radix point. I don't know who makes these words up. Anyway, that's the radix point, which is like the decimal point. And then, so we may have bits to the left of that, bits to the right of that. Okay? Bits to the left of that are associated with powers of 2. Bits to the right of that are associated with negative powers of 2. 2 to the power negative 1, 2 to the power negative 2, and so forth. Okay? And so the fractional representation, n and q, or it's often n comma q, or sometimes n point q, and n here refers to how many points to the left of the decimal point. Q refers to how many points to the right of the decimal point. Okay, so that's a very common. That's the notation that we use for fractional numbers, and so we actually have a notation. N and Q refer to the number of bits before and after the radix point. So if we look, for example, at this number 5 3/4. 5 3/4 you can express as a binary this way. So 5 is actually this portion. The 3/4 is given by this expression. Okay, I can represent that in what is called floating fixed point 1.7, which is a standard. This is actually a standard for defining binaries with fractional portions. Okay, and in this case, I have this number, and m here is the number of shifts required to put this back in the original form. So notice it's a positive 2. Positive 2 means I shift 2 points to the 2 places to the right. The radix point 2 places to the right. Okay, this value here, 2 7/8, has this binary representation. Okay, and if we notice, this is now the floating point 1.7, where I have one decimal point. I mean 1 point to the left, and then 7 to the right. So altogether 8 bits. Altogether 8 bits. So that's part of the reason why F1.7 is used. The 1.7 refers to the fact that we have one decimal point, one thing to the left of the decimal point, 1 and 7 to the right. Okay, and notice in this case, to get from here to here, I shift left by I shift the decimal point by 1, not the decimal point, the radix point. Okay, this number is given here. I can do it in the 1.7 notation this way. Notice I've added some zeros to fill in over here, and this requires a shift to the left of the decimal of the radix point. Okay, so really in converting a number to this fractional binary, it's very common to use the 1.7. It's very common to shift the numbers around so that the highest bit is a 1. It's always a 1. Okay, so notice in all of these it's always, and I keep track of how many shifts I had to do to make that happen, or how many shifts are required to get it back to the original value. Now, this value, 63/64, this is the value I get, and so I pad with zeros here, just like I've padded with zeros here to get a full 8 bits. In this case, 1/3, I actually get repeated values. Okay, so 0, 1, 0, 1, it repeats. 0, 1 repeats. Okay, so I can write that in this notation this way, where I'm truncating the repeating parts. And again, I'm shifting. 1/5, notice I get repeating, but I get 4 bits that repeat. So 0, 0, 1, 1, that pattern repeats. And so, and this requires a shift of -3, and again, I just truncate. 1/10, I actually get 4 values also that repeat, but notice I have to shift 4. Notice these two guys are exactly the same, but the only difference is the shift is different. And if you notice the difference between these two guys, the difference is this is 1/2 of that. So I get the exact same floating point representation. The only difference is the shifts. Just like over here, this value here is 1/2 of that. So I get the exact same floating point representation, fixed point representation. The only difference is the shifts. So I need to keep track of shifts. I need to keep track of the fixed point value. Okay, so this is one way of taking a number and putting it into the fixed point notation. Now, suppose I have two binary numbers, and I want to multiply them. How does that work? Okay, well, you do multiplication with binaries just like you do multiplication with decimal numbers. Okay, so we can go through and do that multiplication. So I basically take this 1, I multiply through. Well, when I multiply something through by 1, I just get that same something back, right? Notice I'm ignoring the decimal points at this point. When I multiply through by 0, I just get zeros. 1, I just get 1s, and so forth. I just go all the way along, and I just keep getting these things. So notice, whenever I have a 0, I actually get a row of zeros. Whenever I have a 1, I just get the whole number in there, and then I keep shifting this thing to the left and adding zeros to the right in order to get the right placement. And then when I'm all done doing this, I add. So 1 with all zeros just gives me a 1. Here I have all zeros, that gives me a 0. Here I have zeros, and I have 1, 1, that gives me a 1. Here I have a 1. Here I have a 1. That adds up to 2, which is a 0, carry the 1. So there's actually a carry here. Okay, so when I carry that 1, I now have a 1 and a 1. That's going to give me a 0. I'm going to get another carry, and so forth. And so I need to keep the carries going. Okay, I need to keep the carries going. And sometimes when I add a column, for example, here, I'm going to add these two guys together along with a carry. So that's going to give me 2 plus 2, which is 4. So the carry, which is 4, doesn't actually go into the next column. It goes into the column. It goes into the column after that, okay? Because it's a 4, which is actually the bit beyond that. So that's actually, it's kind of interesting when you have that kind of thing. So I get a 0, and coming down here, and so forth. And so I just keep going. I have to keep track of my carries, and this is the number that I get. When I'm all done, I look at the number of places after the radix point. There's 1, 2, 3, 4, and I take that number, the result that I get, and I put my decimal place, my radix point 4 in by 4. And so that's the result. So it's just like multiplying two numbers using the standard longhand multiplication. Just now I'm doing it using binaries, and in some ways it's actually much simpler. Okay, the tricky part is you have this long column of things to add. Okay, so to keep track of that addition. Okay, what about a fixed point multiply? So now here 1.7, this is the fixed point 1.7, 1 bit to the left of the decimal point, 7 following, multiplying by 1 decimal point on the left and 7 after. So what happens when I multiply those two things together? So this is the form that I get here. This is the form that I get here. Okay, so I'm multiplying these two together. What is the result that I get? Well, this is what I can expect. I can expect to get 2 decimal places to the left and 14 decimal places to the right. Okay, that is 7 places here, 7 places here. If I move over, I'm going to get, in general, 7. But these are 8 bits. These are 8 bits. When I multiply 8 bits by 8 bits, I'm going to get a 16-bit thing. So altogether I need 16 bits. So in general, the result is something in the fractional form 2.14. 2 bits to the left of the radix, 14 bits to the right. Okay, so in general, when I do a multiply, I expect that's the result I get. Okay, so this is the basic background behind fixed point multiplies. Okay, is generally we want to get things into a form where we have a tool that we can use to do the multiplication. And the tool that the Arduino gives us, the ATmega 328 processor, is that command fmul. There's also fmul-s, fmul-su. Okay, but fmul, I have two registers that I can use that I have to pass it. So floating or fixed point multiplication. I have a destination register and a source register. Actually, this is not the destination register, but anyway, that's how it's defined here. These two registers cannot just be any registers, and they can even be just high registers. 16 to 31. They actually have to be 16 to 23. So we're definitely limited as to what we can use for registers here. Okay, so these registers then, 16 to 23, both registers are assumed to be in the fixed point 1.7 notation. Okay, so that's what's assumed when you do this. Okay, the output of this product is put into registers 0 and 1, and it's put into the form 1.15. Okay, not 2.14 like we would expect. Okay, it's not in this form. It's not in this form like we would expect. It's in this. That's the form that it returns. So if you want the actual correct value, you actually have to do a left shift to get it into this form. Okay, but the important thing is when you do multiplication, remember we had to keep track of all the shifts to get it into the 1.7 form. Here's one more shift we have to take into account and remember. Okay, now fmul is designed to be used for signed numbers, R, D, and RR. Unsigned numbers. These are for signed numbers, and this is for mixed signed and unsigned. So that's just like mul, except it's fmul. And really, it's doing exactly what you would expect a multiplication to do. So it's, but you just need to keep track of what is returned and what do I need and how do I work with what I return. Okay. To do a 16-point multiply, we would do something very similar to like what we did for 16 by 16 multiply with just integer multiply. So it's very similar. The process that we go through using signed, keeping track of which bytes are signed, which ones are unsigned, and so forth, and using the appropriate add, using the appropriate mul, fmul-s for signed, fmul for unsigned, fmul signed and unsigned, fmul signed and unsigned. So this process goes through and takes into account all the 4 terms that you need to get the full multiplication. And so this is the approach that we would use to do that kind of multiplication. 16 by 16 multiply. Now, as an example, suppose I wanted to multiply these two numbers together. So this number is represented this way, which in the f1.7 is this form. Okay, and notice I've had to do 2 shifts to keep track of that, to get it into this form. 3 7/16 can be written this way, which in f1.7 is this. Actually, I need to put some more zeros in here. And I have to shift 1. Okay, so I take these two numbers, I load them into registers 18 and 19, and I do the fmul of 18 and 19, and now I can move the result back into registers 18 and 19. So this is how I would actually do that, and it would multiply these two numbers together. Now, the question is, if you were to work this out, what is the result you would get, and what is the result you're expecting? Okay. So, in all of this, it's in order to properly express the result of this kind of a product. Okay. So the floating point, fixed point with n1 to the left, n2 to the right, m1 to the left, m2 to the right. To express this type of product, where n1 and n2 is a total of 8 bits, m1 and m2 is a total of 8 bits, we generally need to expect a 16 by 16 result. So a general multiply like this is going to require 16, in general, 16 bits to the left of the radix, 16 bits to the right of the radix. And the way you see that is if n1 is 8, if n1 is 8 and n2 is 0, and similarly with m1 and m2, then that product is going to require 16 bits to represent it. Okay, and actually, even if this is 7 and this is 1, it's going to require more than 8 bits. Okay, and so generally, since we do things in terms of bytes, it's going to require 16 bytes, 16 bits to the left of the radix. And similarly, if this is 1 and this is 7, this is 1, this is 7, in general, that's going to require 14 bits. So we need to expect that the overall result of a product like this is going to take a 16-bit, 32 bits. Okay, so that's the result that's going to be required when you multiply a general number like this. When I multiply two fixed point numbers, in general, I need to expect a 16 bits to the left, 16 bits to the right. Now, many of these bits, especially the leading bits, may be 0, and the bits at the end may be all 0, but I can expect that. And so the important thing is, remember, when we get our number into these forms, we need to keep track of shifts, and so it's important to keep track of those shifts. The F mul or F mul S or any of those multiplications, they don't keep track of any of that for you. You have to do that yourself. So that is an important thing that you need to keep in mind. So this is the very rudimentary level of fixed point math. There's much more that could be said, much more that could be said about math in general, doing math on the Arduino. But all good things must come to an end. And so this series of lectures is coming to an end. Thanks for watching.